Great, thank you. Thank you very much for the nice introduction. It is a pleasure and an honor to contribute to the program for the workshop. And today, as Domenico said, I was planning to talk about the probabilistic analysis of neural networks. And actually, this is part of a larger effort that we have at NASA Ames, which involves formal analysis and deriving formal explanations for the behavior of neural networks. So I decided to give an overview of our overall project, and then I will also give, of course, details about this particular aspect on probabilistic analysis. So our work is concerned with the analysis of artificial neural networks, which you probably already know are computing systems inspired by the biological neural networks in animal brains. They consist of neurons or computational units organized in multiple layers. And for the purpose of this talk, it's important to know that neurons can be active or not. And the last layer contains decisions in the case of neural network classifiers, for instance. And these neural networks perform feature extraction and also input transformations. And basically they learn, meaning progressively improve performance to do tasks by considering labeled examples. They can represent complex nonlinear relationships. And in our work, we have looked at feed-forward neural networks with piecewise linear computations. And in particular, we have looked at neural networks with ReLU activation functions that apply comparison with a threshold, typically 0, and then they forward either the value if it's greater than 0, or if it's less than 0, they just forward to the next layer 0. Neural networks has found many applications, for instance, analysis, speech and audio recognition, medical diagnosis, but of course at NASA we are interested in applications in autonomy. For instance, neural networks have been used as perception modules in self-driving cars or in controllers for unmanned aerial vehicles. And with this increased use, of course, comes safety and security concerns. And I list here some of the concerns that are of particular interest to my research. So it is well known that there is a lack of robustness, meaning that small, imperceptible to the human eye changes to an input may lead to misclassifications. And this can happen even for highly trained, highly accurate networks. So for instance, on the right-hand side, I show a picture of a street sign, which was modified by applying some stickers to it, and then a neural network may mistake it for a birdhouse. Or as another example, there were some experiments published that an image of a traffic light was modified by changing 11 pixels, and then a neural network would mistake it to be an oven. And of course, with this, yeah, sorry, I'm just trying to move the screen. There is also lack of explainability, meaning it is not well understood why a network gives a particular output. Essentially, these neural networks are black boxes, and it is not clear why a network performs as expected, and this may pose a problem, for instance, to certification of systems that use neural networks. And it would be very hard to, for instance, place blame on the decision of a neural network in case of an accident. And another serious challenge for the analysis of neural networks is scalability. Neural networks are very large. They are highly interconnected structures and often have huge input spaces. And these characteristics prevent thorough verification and testing. And I would say also that typical heuristics that are developed in the software engineering and the programming languages communities to target finding bugs in general purpose software do not necessarily apply to neural networks due to these characteristics. And another challenge that I list here, which is less studied, but we believe is equally important, is lack of intent. So as I said, neural networks learn from examples without a high level specification. And while traditional safety critical software is developed typically in a top-down manner, you start with high-level requirements and then design and code, and you have clear traceability all the way from requirements to code. We don't have such requirements for neural networks. And this, of course, poses a problem to the formal verification of them. And basically, the challenges that I listed here are applied to train networks, and this is what I have been doing in my work and with our collaborators. But I also listed here some other challenges that are also very important, and I think the community should address them. And they concern about the data itself that, for instance, is used to train a neural network. So when would we know that we have enough data? Or what about if the data is unreliable? The labels may be incorrect, or maybe they were maliciously poisoned. How can one discover that, and how can remedy for such problems? These are open questions that need to be addressed. There is also a problem of bias in the data that needs to be eliminated in order for the network to be fair. And in general, these neural networks involve large amounts of data. They may become obsolete. They need to be updated, and one need to think about carefully about the data management aspect. And I listed here these challenges, but actually I would like to hear also your feedback, and if you agree. So perhaps I'm missing some important points, and I would be happy to discuss about that. Can you still hear me?
Yes.
Okay, my connection is a bit unstable, so please let me know if you no longer hear me.
Okay.
Okay, so to address these challenges, we have a project at NASA Ames called SafeDNA, Safety of Deep Neural Networks, and I listed here the link to the website, so please feel free to visit it and to find more about our work. So this is a project that explores techniques and tools to ensure that systems that use deep neural networks are safe, robust, and interpretable. And I am working with collaborator, Divya Gopinath, who was my postdoc at CMU, and now she's a researcher at NASA Ames. And we have many collaborators, and I listed some of them here. The list is growing, and again, we are very happy to collaborate. So again, please contact me if you are interested in a collaboration. And I'm listing here several of the research directions that we are following in our project. So we have developed symbolic execution techniques for neural networks. The idea there is that we view the activation functions as if-then-else instructions in a typical imperative program, and then symbolic execution could be applied to neural networks, similar to how it is applied to imperative programs. But of course, there are scalability issues, and we address them in a paper that was published at ISSRE last year. Also with the Stanford collaborators with Clark Barrett's group, we are investigating parallel and compositional approaches to improve formal SMT-based verification. And we have an upcoming paper at FMCAD on improving Marabou, which is a tool that they developed for the SMT constraint-based verification of neural networks. We have also done work on property inference for neural networks, and I'll expand on it during this talk. And currently we are working on applying automated program repair techniques to neural networks. I will also talk about probabilistic reasoning for neural networks, and this basically follows also a talk I gave at SIMS 2 weeks ago, which was also an invited talk. And we have also done some work on deriving system-level explanations for neural networks using the Cynic probabilistic programming language. And this is joint work with UC Berkeley, and it appeared at CVPR, which is a computer vision conference. And the overall goals of our project include providing strong guarantees with respect to safety and robustness for neural networks, with particular emphasis on autonomy, as I already said. And we also want to obtain explanations of neural network behaviors, and in particular, we want to provide a formal or mathematical justification for such explanations. And in general, we aim to improve testing, debugging, and maintenance of neural networks. And today I want to review some of our recent advances. So I'll talk about the property inference for deep neural networks, and this was done together with Divya Gopinath and also Hayes Converse, who was a summer intern who visited us for 2 years. He was a student of Safras Khurshid at UT Austin, and also with Ankur Tali, who was at Google at that time. And then I will talk about a programmatic and semantic approach to explaining and debugging neural network-based object detectors. This is joint work with Edward Kim and Sanjit Seshia from UC Berkeley, and again with Divya. And finally, I'll give more details about the probabilistic analysis of neural networks. So in this first work that I want to highlight, which is concerned with property inference for neural networks, our idea is to infer likely properties of a neural network by observing the execution of the neural network on the data, let's say on the training set. And this is similar to, for instance, DICON, if you are familiar with it. And then once we infer these properties, we then try to prove them using a decision procedure. And for instance, we use the reluplex system from Stanford. And the idea is that the piecewise linear activations of the neurons in a neural network are equivalent to conditional statements in traditional programs, and hence the logic of the network can be captured by the on-off activation patterns of the neurons. So the idea is that we run the network on the data from the training or the test set, we observe these activation patterns, and then we organize them in such a way that we get compact constraints, which we then try to prove using reluplex. So to give more details, so what is exactly a property? Our properties are similar to contracts, meaning are of the form pre implies post, where pre, which is sigma in our case, describes a safe region or values that lead to the expected behavior of the network. So sigma in our case is a constraint in terms of on-off activation patterns of neurons in the network, and P is a post condition, which is the, as I said, the desired output behavior of the network. For instance, that it can show that the network has some prediction. And we have looked at deriving these kind of sigma properties, both at the input level, but also at some intermediate level, which we call layer properties. And the idea there is that, as you may know, a neural network works by extracting high-level features from the inputs and then applying several transformations over them. So we hope with these layer properties at some intermediate layers to capture properties over these high-level features. And we have two methods to compute these input and layer properties. So in the first case, we use a form of symbolic or concolic execution to collect constraints over the inputs, and then we have an iterative relaxation of the constraints. And until we get preconditions that imply the output properties. They are not exactly like weakest precondition, but usually they are stronger preconditions that we can compute. And since they have a precise mathematical representation, and actually they define convex regions in the input space, we can also apply several transformations over them. So for instance, we use LP solving to compute boxes of solutions for them. And they can then examine to see exactly what these preconditions mean. And I will show some examples. And then for the layer properties, we apply decision tree learning over the on-off activation patterns that were collected by running the network on the training data. And then once we get these patterns with high support, meaning many inputs from the training data satisfy them and lead to the same output, then we try to prove them with reluplex, and if that doesn't hold, we would then refine them until we get such properties. And on the right-hand side, I show an example for a simple neural network, and below it, a pictorial representation of an input property that basically would be a conjunction of constraints representing the activations at the first layer, and together they would, we could prove that all the inputs satisfying those constraints represented by the blue triangle lead to the same class. And we found that these inferred properties have many applications. So first of all, they provide some form of robustness guarantees, meaning that we know that in the region characterized by the constraints that we infer, the network will have the same class. So in some sense, it will be robust. And we can, of course, find adversarial examples, meaning the examples that are very close to inputs that are classified correctly, but they are misclassified. And these are basically the counter examples obtained with the reluplex tool. And also we view these properties as an effective formal mathematical representation of the input-output behavior of the network. So they can be seen as an explanation that also has a formal guarantee, an explanation for the neural network behavior. And why I say it has a formal guarantee, because we know that all the inputs that satisfy the constraints that we infer lead to the desired property. And we can also use such properties to build simpler models in a form of distillation. For instance, if we derive some layer properties that we know lead to the same output, either through proofs or perhaps if the proofs are too expensive to complete through a statistical analysis, we know that the inputs that satisfy certain activation patterns lead to the same output. So we can use such layer properties to cut the forward propagation, forward phase in the neural network to improve the inference time in a neural network. And we can also use the layer properties that we derive to decompose hard proofs for neural networks, and I'll explain that a bit more. So what I show on the right-hand side are some pictorial representation for the solution spaces computed for the properties that we inferred for neural network that was developed for the popular MNIST data set, which is a set of digit images, and the purpose of the neural network is to classify them. So it has 10 output classes corresponding to digits 0 to 9. And then I show that on the top, for instance, that we show basically the minimal and maximum values computed with our approach for, let's say, for images of that lead to a 2. And then the developer perhaps can examine them to extract more images and to make sure that this is what is expected. And also we can do the same. We can extract properties that lead to misclassification. So for example, I show an image of 1 that is misclassified to a 2, and then we collected basically the constraints around this image, and then we show the minimum and maximum values of other similar images that also lead to 2. And you can imagine that a developer can derive more such images and use them to retrain the network, perhaps to correct this misclassification. I will now expand a little bit on an application to ACAS Xu, which is a safety critical collision avoidance system for unmanned aircraft control. And this is a network that has 5 input attributes, which basically come from sensor data about the ownership, and they include several parameters: range, angle of intruder relative to ownership, heading, angle of intruder with respect to ownership, speed of ownership and speed of intruder. And we analyze the network with 6 hidden layers and 50 ReLU nodes per layer. And the outputs of the network contain 5 labels: clear of conflict, weak left, weak right, strong left, and strong right. So these are basically the advisories that the network gives for the ownership in order to avoid collision with other aircraft. And here are some of the results we obtained for ACAS Xu. So for instance, with our techniques, we were able to discover novel properties for the neural network, and then they were validated by the domain experts. And I list here some of the properties. I will not read all of them, but this is an example that if the range is within certain values and the other parameters have certain values, then the turning advisory is clear of conflict, and so on. So basically this experiment demonstrates that we can derive automatically properties that make sense so to the domain experts. And actually for ACAS Xu, they do have high level requirements, because actually the neural networks were developed based on a table based solution, and they wanted to use a neural network in order to obtain a more compact representation of the decisions that originally were recorded in that table. So they do have high-level requirements, and they are all of the form A implies B, where A is some constraint over the inputs, and B is an advisory. And proving such properties can be very difficult. So for instance, in Marabou, or Reluplex, several of these properties would time out. But then we were able to use some of our layer properties, sigma, to decompose these hard proofs. So for instance, in order to prove A implies B, we would first check A implies sigma, and then sigma implies B. And the idea would be that A implies sigma would be proven only on part of the network. So on the first layer of the networks up to layer on which we derive sigma, and similarly sigma implies B would be proved on the second half of the network. And this would be, of course, cheaper because it leads to a smaller number of constraints in the Reluplex tool, for instance. And with this technique, we were able, with this kind of compositional approach, we were able to obtain significant speed up and to check properties that timed out with monolithic verification. And you can find out more details about our approach in our paper that was at ASE last year. So please feel free to read it and contact us for comments. So now I wanted to highlight another technique that we developed recently. And as I said, this work is based on extracting explanations of a detection module of an autonomous car. And this appeared at CBPR. So the key idea is to leverage high-level semantic features encoded in a CNIC program to derive rules or sufficient conditions that explain a module. So to give a bit of background, so we analyzed this detection module, which is basically a convolutional neural networks that takes images of road scenes, and then the output is a set of bounded boxes around the cars and obstacles that are encountered on the road. And this information is supposed to be used by an autonomous vehicle to, of course, its controller to avoid obstacles. And it is very difficult to test and debug and understand such modules because, as you can imagine, the input domain is huge. So basically it's the set of all the possible road scenes that a car can encounter. So our goal was to help developers understand and debug such networks by looking at higher level features. So what are the higher level features in such road scenes? They are cars that have particular makes, and they are perhaps at a certain angle from the sidewalk. There are intersections. We also have light conditions, weather conditions, and so on. So ideally, one would want to reason in terms of these higher level features, not in terms of pixel values that are in the images and that are input into the network. So what we did in this work, we started with user scenario, which is written in this probabilistic CNIC program that defines constraints and distributions over these high-level features. And from this scenario, CNIC is able to generate vectors of feature values, which are then input into a simulator whose renderer is used to generate realistic images that contain those high-level features. And then our goal is to refine these user scenarios to either stress the module to increase its rate of misdetection, or on the contrary, to increase its rate of success. So in the first case, we want to generate more refined rules that show when the detector performs poorly, so that the developers can understand and debug the module and perhaps use the refined rules that we generate to generate more images and retrain the module. Or on the contrary, with rules that increase the chance of correct detection, they would help us to understand why the detector behaves as expected. So here on the slide, I show a rule in red for that increases the chance of misdetection. So if the certain coordinates and the distance to another car and the car model, the model of the car in front of the own car is a particular brand, then apparently the detection module behaves poorly. Or on the contrary, if for some particular coordinates, the detector works particularly well. So the benefits would be to better explain and also to better debug the module. And I show here some of the results. So we started with, on the left-hand side, I showed the rules for correct detection. So we started with some scenario that, for instance, for scenario 1, the detection module had a 65.3% success rate. But by refining it and adding these extra rules that we derived automatically, we were able to increase the correct detection to 89.4%. Or on the contrary, for the same scenario where the misdetection rate was 34.7%, we were able to increase it to 87.2%. So these rules would then help the developer understand what went wrong with the neural network. And we have several techniques to derive these rules. Again, we use some form of decision tree learning and also a method called anchors. And we have box case, we also use the on-off activation patterns that I described in the previous part of the talk, to try to focus these scenarios on outputs of interest. And again, if more details will be found in our paper. So now going to the third part of the talk, which was also supposed to be the main focus of my presentation at the workshop, I will talk a bit about the probabilistic analysis of neural networks. And this was joint work with Divya Gopinath again, Hayes Converse, and also Antonia Filieri from Imperial College London, who visited us last year. So the justification for this work was as follows. So we have done a lot of work on trying to derive and also to prove properties of neural networks. And we have used Reluplex and Marabou from Stanford, but actually there is an active area of research, and people try to use many tools, to develop and use many tools to prove properties for neural networks. But we have found that properties often do not hold. And actually the majority of the tools are applied to pointwise robustness checks, because such checks in some sense make sense. General properties are hard to come by. As I said, often neural networks don't even have general properties. But these pointwise robustness checks only output binary answers, and they lack detail. So we don't know if a robustness check fails, how often the network would fail. And this may be unsatisfactory for safety critical domains. And also, verification tools do not scale. As I said, Marabou or Reluplex would have trouble to scale to large networks because essentially they reason about constraints collected over the network, and for very large networks, this may lead to scalability issues. On the other hand, we think that perhaps probabilistic properties are more natural for neural networks because such neural networks are approximate in nature, and people use them and expect them to behave correctly most of the time. And it is fine if they fail some of the times. So for instance, accuracy, which is used to measure how a neural network generalizes, is essentially a probabilistic properties. So probabilistic properties are usually checked or could be checked with statistical methods, which of course scale to large networks, but they provide no guarantees. And also they tend to ignore rare events, and such rare events may be important, rare meaning low probability events, and they may be important for safety critical domain. So in our work, we wanted to investigate a probabilistic analysis, which is done through amplifying sampling campaign. And the goal would be to increase the impact and also to provide a precise mathematical measure of the confidence in the results. And the way we obtain this amplification is again through a form of symbolic or other concolic execution along the samples, and then applying volume computations over the constraints collected with the samples. And more specifically, what we do, again, we collect neuron activation patterns along each sample. And in this way, you can imagine that one sample is actually a representative of all the samples that follow the same pattern. And then the activation patterns obtained from one sample is appended with all the decision conditions one by one. And in this way, one activation pattern is amplified to multiple constraints, one for each decision condition. So what does this mean? It means that, let's say, if we execute a sample through the network and it has a particular on-off activation of neurons through the networks, and it may lead to some decision, it's possible that another input that follows the same activation might lead to a different decision, yeah, because the decision conditions are added at the last layer in the network. And we can catch these cases by just examining the first sample. So in some sense, we anticipate errors by looking at samples and appending these conditions. And we also have a way to perform early rejection of samples, and this allows increased scalability. As a parenthesis, of course, our techniques are still not scalable to very large networks, but we hope this is a first step towards that direction. So, as I said, the technique performs symbolic execution over concrete inputs. We observe the activation patterns and we organize them in a tree data structure to keep track of the activations that were explored so far and to reject inputs that add no new information. So for instance, an input that leads to a previously seen activation will be discarded and no longer analyzed. And we also have a way of pruning the trees where we keep track of the children in the tree, and when all the decisions or all the activations below a node have been explored, we would just prune that part, and in this way we could perform an early rejection of samples. So as I said, we add the decision conditions after we collect the activations in order to achieve this amplification, and we compute volume of constraints corresponding to activation patterns appended with the decision conditions. And we have stop at a user-defined criterion such as coverage, number of paths, or rejection percentage. And this is similar to previous work on probabilistic symbolic execution. And I have done such work, and also other researchers have published this work, but we have adapted it to the particular characteristics of neural networks. For instance, in our rejection tree, we take advantage of the fact that all the checks corresponding to activations at particular layer are independent of each other. So we can use that to develop a more efficient data structure than a simple symbolic execution tree. And for volume computation, we use off-the-shelf solutions. So for instance, we use DaVinci, which is a tool that computes volumes of linear constraints over floating point numbers. And this is expensive in practice, but we have developed some heuristics to address some issues. For instance, we can sort activation patterns by hits versus a new set of inputs to cover more space quickly. And also we propose novel use of interval solving. In particular, we use RealPaver, which is capable of solving very large sets of constraints by providing under and over approximating solution boxes. And once we obtain these boxes, we are able to compute estimates of the volumes of the constraints. And to give a bit of information about the input distributions that we can handle. So again, if we assume uniform distribution over the inputs, meaning that all the inputs to the network are equally likely, then we can compute the probability of a decision D by taking the volume of the constraints for the paths that lead to D and divide that by the volume of the full domain, where the full domain is assumed to be finite, but could be very large. And we can also handle arbitrary non-uniform distributions by partitioning the input domain and creating histogram distributions of the form SI-PI, where SI is constraint characterizing a subset of the input domain, and PI is a probability. And then the probability of the decision D is computed using this formula on the slide, where AC contains the activation conditions together with the decision conditions leading to an event D. And we can also compute mathematical notion of confidence in the results, which is simply the percentage of the input domain which was covered by the analysis. And we have implemented the techniques in a tool that we call Space Scanner, and we have used it for the robustness or sensitivity analysis for ACAS Xu, which I already described a bit earlier. And the same tool can be used for analyzing fairness in decision-making networks, but I will not cover that in this talk. And for evaluating local robustness for ACAS Xu, we perform checks of this form. So for a given input X, we want to check that for all other inputs X prime, which are within a certain distance of each other, measured in Euclidean distance, for instance, or some other LP norm. So if they are within an epsilon of each other, we expect that the decision of the network to stay the same. And this could be done formally with Reluplex or Marabou, but the results will only indicate that the adversary is present or not. while in our work, we try to quantify how robust or sensitive is a network to perturbations. And for ACAS Xu, actually, we use domain-specific knowledge, and we only varied the first two parameters of the network. So this made the problem a bit easier. And I list here some of the results. So we used 5 inputs per label, and we relaxed the first 2 dimensions by 5%. So we relaxed them with respect, this is the relaxation to obtain more samples within the epsilon that I described on the previous slide. So we generated 10,000 inputs, and then I show some statistics. For instance, we have an average rejection rate of 91%, meaning that our rejection tree works and many samples follow the same activations. We also obtained clear confidence values. The volume computation time is 2.68 per minute. Which is still a lot, but it's worth noting that the samples can be processed in parallel. So the technique is highly parallel and could benefit from parallel frameworks. We also identified areas in the input where the network lacks robustness. And perhaps the most interesting result is that although statistical analysis produces comparable results, it also misses certain cases when the probability of misclassification is non-zero. So for instance, for an input that was supposed to lead to label 4, we our technique found a non-zero probability for inputs that are similar and that lead to label 0, while the statistical analysis will simply compute probability 0. And another instance is for an input that was supposed to lead to label 1, and so on. So although these probabilities are very, very small, they might be important for a safety critical domain. And to elaborate on more results, I'm not sure if I have enough time, but I will try to wrap it up.
Corina, you have a couple of minutes.
Yes, okay. So we found the network to be highly robust in assigning clear of conflict decisions. And also we found it to be more vulnerable to adversarial perturbations for weak left, and strong right. But we also performed a form of targeted robustness against misclassification to certain advisories. So when the desired advisory is weak right, and we found that an adversarial advisory will only be strong right or clear of conflict, but it cannot be weak left or strong left. So this suggests that the network is pretty robust or is well prepared to be used in the safety critical domain. So when the advisory should be right, the network will not tell the on-chip to turn left or vice versa. So to summarize, we think probabilistic properties are natural for neural networks. Statistical techniques are scalable but do not provide guarantees and may miss low probability events. And we believe that techniques that would work with amplifying inputs have the potential to complement these statistical techniques by giving confidence measures and computing precise probability estimates for the low probability events. And it is useful for robustness and fairness analysis. And just to summarize some of our ongoing work, we are we are investigating model counting techniques to further quantify likelihood of rare events, and also to try to quantify the learnability of a model. We are working on automated debugging and repair for neural networks, where we take low accuracy models or models trained with poison data or that are vulnerable to perturbations, and we try to patch them to correct for these cases. And then we are also interested in relating neural network properties to system level properties of autonomous system. Thank you very much, and sorry if I ran out of time. This would complete my talk.
Thank you, Corina. Thank you very much for your presentation. So we have time for some questions, and I invite everyone in the audience to write their question in the Slack channel. And to begin, I will start with a question about the development context in which verification of DNN is or NN is used. Most of the analysis that you show are design time analysis. Do you foresee any application of runtime verification for neural network, or given their nature of this black box characterization, it's a bit difficult to do runtime verification, in your opinion?
Actually, thank you very much for the question. I'm very excited about runtime verification. I think actually I should have added it to current work because I'm really interested in that. I think perhaps ultimately only runtime verification makes sense. So it's very hard to prove properties, and also so I can see. Okay, sorry. So first of all, with the contracts that I showed in the first part of my talk, the post conditions that we can derive automatically. So supposedly we could prove them. So then you could use them as guards at runtime. So whenever you have an input that satisfies the precondition, you can safely use the network, but if an input goes out of it, then you should go into a fail-safe mode. So this was a bit the first idea, but then I would like to look into it, and I think there should be more work into it, where you can imagine at runtime you monitor the confidence that the network has in the results, and in this way perhaps you can also detect shifts in distribution, because the network is good if if the inputs are as expected. But what if the network is used in a context where the environment evolves? So clearly you would need some sort of runtime monitoring there. And in general, a lot of systems that we analyze in reality come from time series. So for instance, the object detection module takes images of road conditions, but in reality those images are correlated, so you'll not expect completely different images from one frame to the next in some sense. So then again, I can imagine one can write runtime monitors that in successive steps of the object detector, you would not have big surprises. So some sort of notion of surprise perhaps could be encoded as a runtime monitor. So yeah, I think actually there is a big potential in runtime monitoring.
Thank you, Corina. I see there are 2 questions coming up on the Slack.
Am I supposed to read them, or how does it work?
No, they are not. They are not being written yet.
All right.
We are running out of time. So what I suggest is that we move to the Q&A for the paper, and then you can answer the question offline in the Slack channel. So
okay, great.
Thank you, Corina.
Thank you very much. Thank
again.
you, everybody. Yeah. So I'll then follow on Slack. Bye.
Thank you. Thank you.